Hi, this topic is called radioactivity. Now, radioactivity plays a large role in our day-to-day lives, and in this topic, we're going to learn all about it. We're going to learn about how radioactivity is used to generate the electricity that we use, how it's used in smoke detectors, how it's used in medicine and treatments like cancer treatments, and how it's used to generate the energy that sustains life on Earth, on the sun. It's really interesting, and it all starts with atoms. You should be familiar with the basic information and the idea of atoms. So let's quickly test ourselves. Copy and complete this table with the name, mass, charge, and location of the three subatomic particles. Pause the video and complete the table. So you should have been able to complete this table. Let's go through it very quickly. Our first subatomic particle, that begins with P, is the proton. Protons have a mass of 1 or a relative mass of 1, a relative charge of +1, and they are located in the nucleus. The subatomic particle that begins with E is the electron. Their mass is much lower than 1. It's actually 0.0005 or 1 over 1835. Unlike protons, electrons have a charge of -1, and they are located in the shells surrounding the nucleus. And finally, we have neutrons. Like protons, they also have a mass or relative mass of 1. However, they have no charge. They are neutral, so have a charge of 0, and they are also located, like protons, in the nucleus. Now, there's a lot of information in this table, and as you know, we can't actually see atoms. So how do we actually know this information? It all goes back to an experiment done by Rutherford, and we're going to take a look at that experiment now. This is known as Rutherford's experiment. Rutherford fired alpha particles, and we're going to come across those later on, at a thin gold foil, only a few atoms thick. Now the alpha particles fired have a positive charge. As he fired the alpha particles at the thin gold foil, he noticed something very strange. Let's take a look and see what happened. In each case, describe the path of the alpha particles in the animation each time it's fired. Let's take a look at what happened. Most of the particles passed straight through. Some of the particles also passed through the gold foil, but they were deflected and moved in this direction and this direction, rather than going straight through. And finally, very few particles, like the last one we saw, rebounded. We could call this path A, path B, and path C. Let's take a closer look at the structure of the atom and really understand why the alpha particles took these three paths. So, as we know, the nucleus of the atom is made up of protons and neutrons. Protons have a positive charge and neutrons have a neutral charge. Therefore, the overall charge of the nucleus is positive. Let's take a look and see what happens to these alpha particles, which are also positively charged. And let's see what happens to them as they pass through the gold foil or pass through the gold atoms. As you can see, these alpha particles simply passed straight through the atom. This shows us that the atom is primarily made up of empty space. The fact that the alpha particles could pass straight through shows that there's nothing blocking them and they could simply pass through because it's mainly empty space. However, these three behaved slightly differently. Let's take a closer look. So as we know, the vast majority of alpha particles could pass straight through. However, these alpha particles behave slightly differently. Now remember, these alpha particles are made up of 2 protons and 2 neutrons, and also have a positive charge. This alpha particle deflected, and that's because this alpha particle had a positive charge, and so did the nucleus. And as we know, positive charges repel. The same thing happened on top. Another alpha particle was repelled as the 2 positive charges repelled each other. And finally, the alpha particle in the middle, in fact, hit the nucleus and bounced back. Let's take a look at this in more detail now. Based on this experiment, Rutherford came up with 3 different conclusions. The first path showed that most of the alpha particles pass straight through without any deflection. This showed that most of the atom is made up of empty space. Path B showed a slight deflection of the alpha particles. This suggested that the atoms have a nucleus which is positive. And finally, path C suggests that the nucleus is very small and is in the center of the atom. This is why very few particles were rebounded backwards. There's one final idea and concept that we need to recall before we move on with the rest of the topic, and that's the idea of isotopes. Hopefully you can recall this from your chemistry learning, but use these keywords, the ones you can see here, and the diagram to come up with a definition of the word isotope. Here we have 3 isotopes of carbon. Note the difference in symbol, and it would also be worth counting the numbers of the different subatomic particles in each case. Using this, come up with a definition of the word isotope. Pause the video and have a go. Hopefully you've realized the difference now. As we can see, the number of electrons remains the same in each case. So we can say that isotopes have the same number of electrons. This is also shown by the atoms having the same atomic number of 6. If we look at the number of protons, which as we know are positively charged, we also have 6 protons in each case. So we can say that isotopes also have the same number of protons. The key difference is that isotopes have a different number of neutrons. We can see that there's 6 neutrons in the first example, the carbon-12. In carbon-13, we have 7 neutrons. And in carbon-14, we have 8 neutrons. Using this, hopefully you can identify the definition. Using this, hopefully you can create the definition of the term isotope. As isotopes are atoms of the same element, with the same number of protons and electrons, but a different number of neutrons. If you can, try and rewrite this definition using the term mass number and atomic number. Pause the video and have a go. So to do this, all you need to do is look at these symbols here. As we know, the one on the top is the mass number, and this shows us the number of protons plus the number of neutrons. The atomic number on the bottom shows us the number of protons, which in atoms is equal to the number of electrons. So our definition would be atoms of the same element with the same atomic number, but different mass numbers. Fantastic. Now, the idea of isotopes is really important in radioactivity because the heavier the isotope is, the more unstable it is. And we often find that heavier isotopes spontaneously break down to form their lighter isotopes. And this is a really important concept in radioactivity that we are going to go into more detail in the coming lessons. That's it. I hope you found this useful. If you have any questions, please do ask.